So far, we have been looking at oscillators and their simple harmonic motion when there are no other disturbances in the system. That means, there is no force being applied from outside or there is no frictional force. So, what you have been looking at is the simple harmonic motion without any external disturbances. What that means is that if I go back to my spring mass system, the only thing that is here is a spring and mass, and the equation of motion is mx double dot is equal to minus kx. There is nothing else in it. Similarly, if I look at the pendulum system where a bob is on a string and it is made to oscillate, the equation of motion that comes out is m L theta double dot is equal to minus g mg theta. There is nothing else that is working on the system. However, in real life, we either apply force on a system, and why we do that is because there is friction. An example of this is, you can think of a swing or a jhula like a simple pendulum, and if you do not do any outside interference, that means if I do not push it periodically, or if I just push it once and leave it, in the first case it will come to a stop, second case again if I leave it, it comes to a stop. So, obviously, the equation that is describing it is neither this nor this, but there is an additional force, right. So, that is to be accounted for. So, we either apply force on a system there is friction, if we do not, the system comes to a stop after some time, right. In the in the first case, when I apply a force, it is known as a forced oscillator. In the second case, when we do not apply a force, but the system comes to a stop, it is known as a damped oscillator, and if a damped oscillator is pushed periodically, it is known as forced damped oscillator. So, in this lecture, we are going to look at free oscillator, that means no friction, under a periodically applied force, what I will call a forced oscillator. And I am also going to look at an oscillator that experiences frictional force. There are going to be two kinds. One of them could be a constant friction, and the other one is a velocity dependent friction. We will consider both cases. It is usually the second one the velocity dependent friction that is referred to as damped oscillator. And finally, we are going to look at forced damped oscillator. The mathematics required is slightly more involved than what we had been doing so far, but I will try to make it as easy for you as possible and also give you a qualitative feel for the system by interpreting terms very slowly. So, let us first look at an oscillator without friction, but being under the influence of a constant force. Let us go back to our example of spring mass system. So, if I have a spring mass system, what I am doing in this regime is I am applying a constant force to it. You have already seen an example of this. The example is when I hang such a system vertically, then there is a constant force mg in this case, and what you saw earlier that in this case the only thing that happens is that the equilibrium point shifts, but the oscillations remain at the same frequency about that new equilibrium point. So, let us now show it explicitly. So, if I have an oscillator which is under a constant applied force, the equation of motion is going to be this. So, minus kx is the restoring force due to the spring, and there is a constant applied force F. So, I am going to have x double dot plus k over m x minus f over m is equal to 0. From now on in this lecture, I am going to refer to k over m as omega 0 square. Omega 0 is to indicate that this is the natural frequency of the oscillator. So, omega 0 is the natural frequency of the oscillator. There is no other force applied. So, later you will see that when I apply periodic force, it is going to be at a different frequency. So, to distinguish from that, I am writing this as omega naught. So, this can be written as x double dot plus k over m x minus f over m, and what I am going to do is now take x double dot plus I will take k, keep m on the left hand side, x minus f over k is equal to 0. I am writing this equation of motion in this form. And now what I will do is, so this is my equation of motion, mx double dot plus k x minus f over k is equal to 0. Now define y equals x minus f over k. Then y dot is equal to x dot, and by this we mean dy by dt is equal to dx by dt, and y double dot is equal to x double dot, by which we mean d2y by dt square is d2x over dt square. And then the equation becomes m y double dot plus k y is equal to 0. This is exactly the equation for a free oscillator, and therefore, the solutions are going to be y t is going to be some constant a cosine of omega t, omega 0 t, plus b sine of omega 0 t, where a and b would depend on the initial conditions. But remember what is y? Y is nothing but x t minus f over k. So, this is a cosine of omega 0 t plus b sine of omega 0 t, and therefore, finally, x t is f over k, which is a constant displacement. Remember, this was in the vertical spring, this was mg over k, that is the new equilibrium point, plus the oscillatory part cosine of omega 0 t plus b sine of omega 0 t. That is the answer. So, nothing really changes in the case where a constant force is applied to an oscillator, except that it starts oscillating with the same natural frequency about the new equilibrium point. Now, I take the second case, and this is where we apply a periodic force, which is time dependent obviously. F t equals some constant f cosine of omega t. I am writing cosine omega t, it could be sine omega t, just depends on where your initial time is measured from, but the results are the same. Why am I calling it periodic force? Because you see, after all, an oscillator is oscillating with certain frequency. So, it makes sense to apply forces in real life which are periodic, which sort of repeat themselves after a time. So, therefore, usually we study these oscillators under the influence of a periodic force. So, equation of motion in this case is going to be mx double dot is equal to minus kx plus f cosine of omega t, where omega is not necessarily equal to omega naught square. I can divide by x m all over and write this as plus k over m x equals f cosine of omega t, which is the same equation as x double dot plus omega 0 square x equals, there is a divided by m here, is equal to f over m cosine of omega t. That is the equation to be solved. Let us see what happens in this case. So, if f is 0, then I have a solution, the equation x double dot plus omega 0 square x equals 0, and the solution x t is some constant a cosine of omega 0 t plus b sine of omega 0 t. A and b will be determined by initial conditions. But now I have f not equal to 0, and I have the equation x double dot plus omega 0 square x equals f over m cosine of omega t. Let us try different solutions. Now, you see, if we take x proportional to cosine omega t itself, then x double dot is proportional to minus omega square cosine omega t. On the left hand side, when I add x double dot and omega naught square x, I am going to get a term which is proportional to cosine omega t. And therefore, this could be the form of the solution. Notice that I cannot, right. Let me also comment here on the side, cannot have x proportional to sine omega t, because in that case left hand side and right hand side will not cancel, or x proportional to some t raised to n. In that case also solutions would not match. Let me explain all this. So, we are looking for solution of x double dot plus omega 0 x is equal to f over m cosine of omega t. If we take x proportional to sine omega t, x double dot would be proportional to minus omega square sine of omega t. Write this, what this proportional to means. I am taking x equals some constant, let us call this c sine of omega t, and this means x double dot is equal to minus omega square c sine of omega t. If we substitute in this equation, I get minus omega square c sine of omega t plus omega naught square c sine of omega t equals f over m cosine of omega t. Notice that left hand side has sine omega t dependence. Right hand side has cosine omega t dependence. So, the two can never match. These two will never match at all times. Therefore, sin omega t cannot be the solution. I will cut it out. This cannot be the solution. This cannot be the solution. Okay? Similarly, we show that x proportional to say t raised to n cannot be a solution. Why? Because in this case, if x says c t raised to n, x double dot is going to be n minus 1 c t raised to n minus 1. And when you substitute this in the equation, you will see that left hand side, right hand side, nothing matches. So, this cannot be the solution. So, x proportional to t raised to n or any polynomial is not a solution. So, the only possibility you are left with for this equation x double dot plus omega 0 square x equals f over m cosine omega t is that we take x t to be some constant c cosine of omega t, because in this case x double dot is going to be minus omega square c cosine of omega t. Substitute in the equation, I get minus omega square c cosine of omega t plus omega naught square c cosine of omega t is equal to f over m cosine of omega t. And this can be satisfied all the time, because we have this cosine omega t term all over the place, which actually cancels. And you get c is equal to f over m omega 0 square minus omega square. So, in dividing, I am assuming that omega 0 is not equal to omega. If omega 0 is equal to omega, then we will deal with that case in a few minutes, but right now let us just focus on this case. This therefore is the solution x t is equal to f over m omega naught square minus omega square cosine omega t. Notice that this has no free parameters that are to be adjusted depending on the initial conditions. So, how do I take care of the initial conditions? The general solution is going to be a cosine of omega 0 t plus b sine of omega 0 t plus f over m omega naught square minus omega square cosine of omega t. I will call this part, the first part, as x homogeneous t plus this I will call x particular t. In short, I will write this as x h t plus x p t. These are notations with the property that x homogeneous, which is a cosine omega 0 t plus b sine of omega 0 t, is such that x homogeneous double dot plus omega 0 square x homogeneous is equal to 0. On the right hand side you get a 0, and that is why I call this solution of this homogeneous equation. And x p double dot, what is x p? X p is f over m omega 0 square minus omega square cosine of omega t xp double dot plus omega 0 square xp is f over m cosine of omega t. This is satisfied. So, this is true for this particular form of the force that we applied on the right hand side, and therefore, we call it x particular. So, when you take x homogeneous plus x particular, right, this has a solution, then you have x double dot is equal to x homogeneous double dot plus x particular double dot, and omega naught square x, when I add this becomes omega naught square x plus omega naught square x particular, and if I add the two I get x double dot plus omega naught square x is equal to x homogeneous, this is homogeneous, double dot plus omega 0 square x homogeneous plus x particular double dot plus omega 0 square x particular. This part we have already shown is 0, and the second part gives me f over m cosine of omega t. So, the true solution we have seen which satisfies this equation is x t equals a cosine of omega 0 t plus b sine of omega 0 t plus f over m omega 0 square minus omega square cosine of omega t. This is the true solution, and now because I have these two a and b coefficients which are not known with any given initial conditions, I can fix these and I have the full solution of the motion. Let me now explain this through a particular example. Let us say we take x at t equal to 0 equal to 0, x dot at t equal to 0 to be 0. Suppose we do that. Now, in the case when there is no force, if there is no force, there is only one possible solution in this, and that is x t equals 0 all the time. After all, the mass was sitting at some position with 0 initial velocity, no force was applied, so it is not going to move. But if there is a force, right, if there is a force f equals f cosine omega t, then my solution x t is a cosine of omega 0 t plus b sine of omega 0 t plus f over m omega 0 square minus omega square cosine of omega t. Now, I have been told that x at t equals 0 is 0. This implies a plus f over m omega 0 square minus omega square is equal to 0, or a equals minus f over m omega 0 square minus omega square. We have determined a. X dot at t equal to 0 is 0. It gives me a sine of omega t at t equal to 0 plus there is an omega 0 with a minus sign plus omega 0 b cosine of omega 0 t plus omega f over minus m omega 0 square minus omega square sine of omega t at t equal to 0. This term, because sine 0 is 0, this term is 0. So, this immediately gives me b equals 0. So, now we found our solution. Our solution of x t is f over m omega 0 square minus omega square cosine of omega t minus cosine of omega 0 t. So, if I take a spring mass system or a pendulum and apply a force which is periodic with a frequency omega t, and this starts at t equal to 0 from its equilibrium position with no initial velocity, the final answer is going to be as given here. It is a combination of two different frequencies. Let us examine this a little further. I am going to now write cosine of omega t minus cosine of omega 0 t as 2 sine of omega plus omega 0 divided by 2t times sine of omega minus omega 0 divided by 2t with a minus sign in front. So, x t is going to look like minus 2f over m omega 0 square minus omega square sine of omega plus omega 0 over 2 t sine of omega minus omega 0 over 2 t, which I can also write as 2f over m omega 0 square minus omega square sine of omega plus omega 0 over 2 t sine of, I am absorbing minus sign here, omega 0 minus over 2 t. I am doing so because I am now going to assume omega 0 is greater than omega. So, the final solution is x t equals a sine of omega t times sine of, let me call this delta omega because this is a small number if omega 0 and omega 1 are close, t, where amplitude A is 2f over m omega 0 square minus omega square, capital omega is omega plus omega 0 over 2 and delta omega is omega 0 minus omega over 2. Let us go to the next page. So, my solution x t is 2f over m omega 0 square minus omega square sine of capital omega t sine of some delta omega t. Notice the amplitude. Amplitude is 2f over m omega 0 square minus omega square. You will notice this omega 0 and omega are very close. This becomes very large if omega 0 approaches omega 1. This is the phenomena of resonance. In a while, I will show you how this resonance occurs and how this amplitude grows if the two frequencies become equal. And the time dependence of this x t is a product of sine omega t sine of delta omega t, where omega obviously is much greater than delta omega. I am assuming that they are close. Therefore, what we are going to have is product of two sine functions, right. One sine function is of a very small frequency, so that is going to be like this. So, this is blue one is sine delta omega t, and the other function capital omega t is going to be a very highly oscillating functions. So, black one is sine of capital omega t. If you take the product, you can see that this amplitude of the black one is going to vary with time, and therefore, if I represent x t on a graph with time, is going to be, let me make that blue one with dotted lines now, it is going to be oscillating like this. So, the amplitude is going to vary. Sometimes the amplitude is going to grow, and that is when the force has really worked on it, because the frequencies are different, worked on the system, and when the force works against the system, the amplitude goes down, and that is, and this happens periodically, and that is precisely what is shown here. So, amplitude goes up, amplitude comes down. Notice that if omega 0 comes close to omega 1, this blue part, the way the amplitude varies, is going to become larger and larger in time, and that means this is going to expand. So, if I have a larger frequency, two closer frequencies, suppose omega 0 is very close to omega 1, then what I am going to have is that this blue part would look like the orange part will just keep going like this. It will come down after a long time, and therefore, the oscillations would grow and come down after a long time, and this is the phenomena of resonance, which I am going to discuss next. So, this is the form of solution when omega naught is not equal to omega, that means the applied frequency omega is not equal to the natural frequency. Let me make you understand the phenomena of resonance. This will arrive from here. X t is given to be 2f over m omega 0 square minus omega square sine of omega 0 plus omega over 2 t times sine of omega 0 minus omega 1 over 2 t. Now, you see I cannot substitute, let me write this in red as a warning, cannot substitute omega equals omega 0 directly in the formula above, because we divided by omega 0 square minus omega square, assuming omega 0 is not equal to omega. If I want to take omega 0 equals omega, then the only thing I can do is, therefore, for omega 0 equal to omega, we take the limit omega 0 tending to omega. In this case, if omega 0 tends to omega, then sine of omega 0 minus omega over 2 t would tend to, if omega 0 and omega are very close, they are becoming close to 0, this will go to omega 0 minus omega over 2 t. This is similar to sine theta going to theta for theta tending to 0. And in this case, omega 0 plus omega over 2 would tend to omega 0. So, the answer I am going to get is x t equals 2f over m omega 0 square minus omega square I am going to write as omega 0 plus omega, omega 0 minus omega, so that I can cancel omega 0 minus omega, times sine of omega 0 t times omega 0 minus omega over 2 t. Now, I will cancel terms, omega 0 minus omega cancels with omega 0 minus omega, this term is like 2 omega 0, and therefore, the answer I get finally is going to be f over 2 m omega 0 t sine of omega 0 t. This is my final answer. So, in the case when omega 0 equals omega, my answer for x t is f over 2 m omega 0 times t sine of omega 0 t. If I think of this first term as the amplitude, you notice that the amplitude increases linearly, and therefore, x t versus t is going to look like and amplitude will keep on increasing with time, and this is the phenomena of resonance. Next, I am going to determine the cases, examples where a harmonic oscillator experiences frictional force, or it becomes damped. First case I am going to take is constant friction. This is a case where suppose I have a spring mass system. On the surface there is a frictional force acting, which is mu mg. So, if it is on a horizontal plane, and what happens to the direction of friction when this mass is moving to the right. Suppose this is x dot, that is velocity is to the right, this is going to be the direction of frictional force to the left F, and when the block is moving to the left, that is x dot, the force, frictional force is going to be opposite to this in the other direction. If this is a constant force, it is not easy to put it directly in the equation taking care of the direction itself, because what you want to finally write is that m x double dot is going to be the restoring force plus a frictional force which is like in the direction opposite to x dot. So, if you want to be mathematically sophisticated, you would actually write it as f times minus x dot unit vector. Okay. So, instead of writing it like this, I am going to solve this problem in by taking care of friction when the block is moving to the left or when the block is moving to the right, and we will apply energy conservation. In this case, energy does not get conserved. What I mean by this is loss of energy due to friction is going to be equal to the change in the energy of the oscillator, and this is what I am going to use to calculate how this motion gets damped. So, let us consider the case when I take this spring mass system. If this is left alone here, nothing would happen because nothing is make it move. If I displace it by an amplitude A from the equilibrium position, let me write it here by amplitude A and leave it. So, what I have done is I have taken this spring mass system, stretched it from its equilibrium position by an amount A and released. So, this fellow is going to move to the left with frictional force acting to the right, and it will keep on moving, keep on moving, keep on moving until it comes to a stop, and in the process it loses energy. The energy it started with when I stretched it is 1/2 k A square. If there was no energy lost, this would have been, the compression also would have been A, but now it is going to be A1. Why? Because the energy has been lost, and the energy now here is going to be 1/2 k A1 square. Whatever the loss in the energy is, that is lost due to friction. So, the change in energy is equal to 1/2 k A square minus A1 square. A1 obviously is less than A because energy has been lost. So, this is 1/2 k A plus A1 times A minus A1, and this energy loss is going to be equal to work done against the friction. And how much is the work done? This is equal to the frictional force F times the total distance moved. Total distance moved, you can see from the picture, is A1 here and A here. So, this is A plus A1. Now, our equation is very clear, and this immediately gives me that A minus A1 is equal to 2 F over K. So, the amplitude has decreased by 2f over k, or the maximum stretch or compression has decreased by 2f by k. Notice that this is independent of the amplitude I started with, and therefore, when it goes back again the decrease in the amplitude is going to be 2f by k. So, in one cycle the decrease in amplitude is going to be equal to 2 times 2f over k equals 4f by k, and slowly the pendulum will keep losing this energy and come to a stop. So, this is the constant friction case. The other case, which is referred to, as I said earlier, as damped harmonic oscillator, is when the frictional force is proportional to x dot. This is like the force you see in Stokes's law, right, or velocity dependence drag. So, I am going to call this equal to b x dot with a minus sign. So, that the equation of motion now is m x double dot is equal to minus k x minus b x dot. Notice that in this case I do not really have to put a unit vector or anything, because whatever the sign of the x dot is, minus b x dot gives me the force opposite to that. So, it is sign is automatically taken care of, and therefore, I am going to have differential equation is m x double dot plus b x dot plus k x equals 0, and this is usually by dividing by m is usually written as x double dot plus b over m x dot plus k over m, recall, is omega 0 square x equals 0, and the term in the middle b over m, the term in the middle is usually referred to as gamma, and therefore, the equation which you will find in the books in the standard notation is written like this. This is the notation in this damped harmonic oscillator equation is written as. So, this is equation of motion for a damped harmonic oscillator. Gamma is the damping coefficient. So, let me write it on the left. Gamma is damping coefficient. So, for a damped harmonic oscillator, the equation is x double dot plus gamma x dot plus omega 0 x equals 0. In this lecture and at your level for 12th grade, we are generally interested in qualitative features of this equation. So, I am not going to solve it exactly, rather what I will show you are some limits and try to get the solution and feel for those motions in a particular way. So, I am first going to consider a case when gamma is much greater than omega 0. What does that mean? That means the damping in the system is quite large. For example, I could take say a simple harmonic oscillating system, right, with some frequency and put it in a very thick liquid, put the mass in a very thick liquid, maybe like glycerine or honey, then it will be highly damped, right, and the motion is probably, you can feel, is that if I leave it, all that is going to happen is slowly it will come to equilibrium, right. So, in this case let us see the solution. So, if gamma is much greater than omega 0. All right. Now, keep in mind that gamma has the same dimension. Let me mention that gamma and omega 0 have the same dimension, that is second inverse. So, I can compare gamma and omega 0 directly. If gamma is much greater than omega 0 and we are talking about small amplitude motion, this is omega square, then approximately I can write x double dot plus gamma x dot is equal to 0. That means d2 x by dt square plus gamma dx by dt is equal to 0. That is going to be my equation of motion, because I can neglect the last term. All right. So, I have the equation d2 x by dt square plus gamma dx by dt is equal to 0. Let dx by dt be denoted as some zt, then d2 x by dt square is dz by dt. So, the solution I have is dz by equation I have dz by dt plus gamma z equals 0, and its solution is z equals some constant e raised to minus gamma t. So, dx by dt is equal to c e raised to minus gamma t, and therefore, x t is going to be some other constant c1 e raised to minus gamma t. What that means is that if I take this mass and leave it from some distance, it is going to just come to equilibrium position exponentially. So, this is x t. If I leave it with some amplitude a, with time is just going to go down in this manner, right, because so initial conditions, if I take some x t at t equal to 0 to be equal to a, this is going to come down as a e raised to minus gamma t. You could actually solve this equation in more detail, but this is a general feature that in this case this is what is going to happen, right. Now, let us try to solve it more precisely. So, this is a case where we have taken this mass and put it in some very thick liquid, so that its damping is very large, and in this case you can see that x t is proportional to e raised to minus gamma t, and the solution looks like something like this, and this is known as the heavily damped oscillator. 2. Let us take the other case, x double dot plus gamma x dot plus omega 0 square x t equals 0, and take omega 0 to be much greater than gamma. Okay. In that case, to a good extent, I can write x double dot plus omega 0 square x t equals 0, and x could be a cosine of omega 0 t plus b sine of omega 0 t. Just for simplicity, to understand the motion, my focus is to understand the motion. Let us take x t to be a cosine of omega 0 t, so that b is 0. What does this motion correspond to? That means we have x at t equal to 0 equals a, and x dot at t equals 0 equals 0. That means what I have done is I have taken this spring, stretched it and left it. So, x t equals a cosine of omega t, omega 0 t corresponds to x t equal to 0 equals a, and x dot t equal to 0 equals 0. So, what we have done is, in this case, I have stretched the spring by some amount a and just left it. Okay. Now, I know if there is damping, the amplitude decreases slowly. So, in this case, when gamma is not equal to 0, A is a function of time, and therefore, x t is going to be A t cosine of omega 0 t. But we want to find A as a function of time. So, what I will do is, why does A change? Just like in the case of constant friction, A changed because there was dissipation of energy because of friction. In this case also, A decreases because there is dissipation of energy due to friction. So, what I will do is find out how much energy is lost due to friction, and that would be related to the change in A. So, force F t in this case is how much? It is B x dot with a minus sign, which I can approximately write as minus B d by dt of A t cosine of omega 0 t. This is not approximate, this is exact, which I can write as minus B dA dt cosine of omega t times omega 0 t times minus plus B omega 0 A t sine of omega 0 t. That is F t. So, energy lost due to F t is going to be equal to F times x dot per unit time. So, this is nothing but the loss in power. So, I can write this here also. So, energy lost per unit time is equal to F x dot, which is going to be minus B x dot square, which I can write as minus B d by dt of A t cosine of omega 0 t whole square. Now, since I am going to make some approximation, since gamma is much less than omega 0, anticipate that dA by dt is negligible in comparison with d by dt of cosine omega 0 t, which is of the form omega 0 sine of omega 0 t, right. So, what we are saying in essence is, just to make sophisticated language, gamma is much less than omega 0. So, 1 over gamma is much greater than omega 0. This means this is nothing but time omega 0 inverse time scale involved with amplitude decrease, and this is time scale of oscillation. So, what it means is that the time scale involved with amplitude decrease is much larger than time scale involved with oscillations. Physically, what it means is, we see many oscillations before observing any significant decrease in amplitude. What it also means is that is why we can talk about amplitude AT as a function of time. Let me explain that. If for 10, 15, 20 oscillations I see that there is hardly any decrease in the amplitude, then only I can say this is oscillating with amplitude AT at a given time. Then after many oscillations, after maybe 3 hours, 4 hours, when 5,000 oscillations have taken place, then I say, okay, now the amplitude has decreased. All right. So, for a given short time, for 10, 15 oscillations, if there is hardly any decrease, and that could be, say, those oscillations take place in, say, 1 minute, 2 minutes, compared to a significant amount of time, say 1 hour or 2 hours, when the amplitude decreases, then it does not really matter that whether I count where do I start the time from and where I end. So, then only I can talk about this amplitude as dependent on time. If every oscillation the amplitude changed, then I would not have been able to talk about amplitude as a function of time. So, all this slide that it explains is that gamma being much smaller than omega 0, I can talk of amplitude as a function of time. For few oscillations it does not really change, for thousands of oscillations it changes, because that is the time scale of 1 over gamma. So, now let us go back to our mathematics, and what we had said that energy loss is equal to minus B x dot square, and x dot I had calculated 2 slides back was d by dt of A t cosine of omega 0 t, which is dA by dt cosine of omega 0 t minus omega 0 A t sine of omega 0 t, and with whatever I discussed just over the last slide, I am going to neglect this term, because dA by dt, let us say 1 over A. So, that becomes the 1 over time or frequency with which the amplitude changes is much smaller than omega 0. So, I neglect that term. So, I can write x dot as equal to minus omega 0 A t sine of omega 0 t, and therefore, energy loss is minus B x dot square. B is nothing but minus gamma m x dot square is omega 0 square A t square sine square omega 0 t. Now, I said that for a few oscillations it doesn't AT doesn't really change. So, when I talk about energy loss, it is no point talking energy loss as a function of every time during an oscillation. More meaningful is to talk about energy loss per cycle. Energy loss per cycle is going to be minus gamma m omega 0 square A square t sine square omega 0 t dt 0 to t, that means over the cycle. Even better, if I want to talk about dE by dt, this is going to be energy loss per cycle divided by the time period, which is going to be minus gamma m omega 0 square A square t 1 over t 0 to t sine square omega 0 t dt, and this sine square average over a cycle is 1/2. So, energy loss d by dt is minus gamma 1/2 m omega 0 square a t square. A t again we mean by for a few oscillations it remains the same, but what is this? M omega 0 is k, so this is 1/2 k a square t, which is nothing but equal to the energy at time t. So, what we see in case of gamma being much less than omega 0, dE by dt is equal to minus gamma Et, or the energy of the system E t goes as some E 0 at time t equals 0 e raised to minus gamma t. That is the solution of this equation. Furthermore, now I also know how the amplitude changes, because my equation is dE dt equals minus 1/2 gamma k a t square, and dE by dt is nothing but d by dt of 1/2 k a square, which is k a dA by dt, and therefore, I get k a dA by dt is equal to minus 1/2 gamma k a square. I can cancel one a, I can cancel k, and I get dA by dt is equal to minus gamma by 2 a, or a t equals e raised to minus gamma by 2 t a 0. So, amplitude changes like this. So, what is happening? With time, amplitude with time goes down as e raised to minus gamma by 2 t. What is my final solution? Is a t cosine of omega t, which is a 0 e raised to minus gamma by 2 t cosine of omega 0 t. Let us see how it looks. Amplitude we said changes like exponential e raised to minus gamma by 2 t, and notice that omega 0 we have been taking is much greater than gamma. So, oscillations take place with much larger frequency, and the amplitude is going down with time like this. So, in the case of light damping, the oscillator is oscillating, and with time its oscillation, its amplitude goes down as shown here. So, this red part is a 0 e raised to minus gamma t. This whole thing, black and red thing together, is a 0 e raised to minus gamma by 2, this is gamma by 2 t times cosine of omega 0 t. This is how the amplitude goes down. So, to conclude this lecture, we considered forced, undamped, oscillator. We considered the phenomena of resonance, and we considered heavily damped oscillator, and we considered lightly damped oscillator, and in between I forgot is constant force on an oscillator, and here also we considered constant damping force on an oscillator, and we qualitatively understood that how the oscillator behaves in all these cases. In the next lecture, we are going to consider the forced damped harmonic